Okay, so for our last bit of this, we're going to talk about inverse functions and compositions. So because the idea of an inverse function is it's supposed to undo the original function, means it kind of like reverses the operators and undoes everything. So something unique happens when we have a function and its inverse and we try to do a composition. So as we see, like I said, a function and its inverse are still inverses of each other, so this isn't going to make a big difference. So if we take f inverse and compose it with f, so f is on the inside of f inverse, what should happen is that we'll just get x back. If we have f composed with f inverse, so f inverse inside of f, we expect also get x back. So for each x in the domain of f and for each x in the domain of inverse of x. So what we're saying here is that one function essentially like addresses x, the other one undresses x. So when one function puts everything on x, then we compose that inverse function, the inverse takes everything back off. So what happens is that we could test if two functions are inverses of each other if we do a composition, and that composition is x. So if I gave us the function f is 5x plus 8, and the composition function would be x minus 8 over 5. The inverse function of the composition, that would be the inverse function. So if we wanted to show that in fact they are inverses, we would just have to do a composition. And it actually doesn't matter which composition you do, because either way it's going to work. So if I do f composed with f inverse, f is the outside function, f inverse is the inside function. So f inverse is just x minus 8 divided by 5. So that would mean that if I'm doing my composition, let me go back. F is going to be 5, x plus 8, and we're just replacing x with 8 minus 8, x minus 8 divided by 5. So we see those 5s are going to cancel. The multiplication of 5 and the division of 5, leaving me with just x minus 8 plus this 8. So minus 8 plus 8. The 8s are going to disappear, and I'm just going to be left with x. I've done it the other way around, so f inverse is composed with f. And then we're putting the f inside of f inverse. Well, we know that f is just 5x plus 8. F inverse is x minus 8 divided by 5, and replacing x with 5x plus 8. So plus 8 minus 8, those cancel each other out, so we're left with 5x over 5. Those cancel each other out, and I'm just left with. So like I said, this is mostly a way to use to test if two functions are inverses of each other. If the composition just produces x, then they were inverses. As another example, we had seen when we did number 5 on the worksheet that when we had g was 3 over x plus 2, that the inverse was 3 minus 2x over x. Or at least that's what we thought. So if we wanted to test to see if we actually had the correct inverse, so is that inverse correct? What we could have done was we could have just done the composition of your functions. So we'll compose g with inverse of g. So that means that we're going to have g, and inside of g is going to be, or all our x's are going to be replaced with 3 minus 2x over x. So g was just 3 over x plus 2, well, x is replaced with 3 minus 2x over x. Okay, so let me just rewrite this without the parentheses. So if we wanted to combine the denominators on the bottom, or combine the two in the bottom, we need to have this 2 have the same denominator. So I could rewrite it as 2x over x. Which means I would have 3 minus 2x plus 2x over x. So this simplifies to 3 over 3 over x. So this is a fraction on the bottom, so I can turn this into 3 times the reciprocal of the bottom fraction, x over 3. And as we see, the 3's will cancel, and I'm just left with x. So this is the inverse of g. So that's part of the reason of doing this composition, is just partly to test to see if we do have the correct inverses. So for number 6, you just have 2 functions. So first you have f and g. F is going to be 7 minus 2x. G is 7 minus x over 2. So use compositions of functions to show that they are inverses. B is fx, this time is going to be x minus 3, and all that is raised to the power of 3. And g is going to be x to the power of 3 plus 1. So take a moment and show that those are actually inverses of each other using the composition of functions. All right, so if we look at A, like I said, we just need to do a composition. Doesn't matter which goes on the inside. So we're going to do the composition of f with g to see if they are in fact inverses. So that means g is on the inside. So that means I'm doing f of 7 minus x over 2. And f is just 7 minus 2 to the power of, or 2 times x. And we said we replace an x with 7 minus x over 2. So we see this multiplying by 2 and this division by 2 cancels. So I'm left with 7 minus 7. So let's do this actually, because I was subtracting this term here. So it's 7 minus x. I distribute that negative through. It is 7 minus 7 plus x. And this equals x. These functions are inverses of each other. Meaning that I could take one of these, I could rewrite this one as f prime of x. Or it's possible that we could just rewrite this one as g prime, f inverse of x, and then we could rewrite this one as g inverse of x. Oh, both those notations sticking in my head. B. Let's do it the other way. Let's say we're going to do g composed of f, just for fun. So we're going to have g on the outside and f is on the inside. And we know that f is just x minus 1 cubed. G is going to be x cubed plus 1. So we're seeing we're getting a cube inside of a cube. This turns into x minus 1 to the power of 9 minus 1. And what we see here is that these, in fact, are not actually inverses because this is not x. So these ones are, in fact, not inverses of each other. So like I said, this is quickly how we can show if something's an invert, if two functions are inverses of each other or not. Their composition would be x. If they're inverses, if it's anything other than x, they are not inverses.